The Pasco wireless motion sensor is a popular tool for measuring the position and motion of objects in physical science and physics classrooms. In this video, learn about the sensor's features, operation, and tips for use in the lab. Use the Pasco PS3219 wireless motion sensor to measure the position, velocity, and acceleration of objects moving in one dimension toward or away from the sensor. View, record, and analyze those measurements in Pasco software, including the general-purpose SparkView and Pasco Capstone programs, and the engaging kinesthetic MatchGraph application, which provides a motivating accuracy score. The wireless motion sensor can connect to the software wirelessly using Bluetooth for low energy, or via USB with the provided cable. Use the same cable to charge the sensor's internal rechargeable battery.
The wireless motion sensor detects the distance to an object using echolocation. The sensor emits ultrasonic pulses from the gold-colored transceiver on the face of the sensor. You'll hear an audible click each time these pulses are sent. The ultrasonic pulses travel out from the front of the sensor in a narrow cone until they hit an object, from which the pulses are reflected back to the sensor and detected as an echo. This process allows the sensor to determine the round-trip travel time of the pulses. Using this time and the speed of sound in air, software calculates the distance from the sensor to the object and reports it as the object's position relative to the front of the sensor. From successive position measurements, the software derives the object's velocity, and from successive velocity measurements, its acceleration.
The wireless motion sensor can detect objects as close as 15 centimeters and as far away as 4 meters, but only if the distant object reflects enough sound back. By default, the sensor measures 20 times per second, but in SparkView and Pasco Capstone, that sample rate can be decreased or increased to a maximum of 250 Hz as needed for your experiment. Note that at high sample rates, the maximum measurement range decreases due to the reduced time between samples available for the echo to return to the sensor.
When troubleshooting unexpected readings from the wireless motion sensor, keep in mind its principle of operation, echolocation. Ensure that the intended target object reflects sufficient sound back to the sensor by aiming the sensor face straight toward the object, making sure that the direct path between the sensor and intended target is clear, and even removing any potentially reflective objects just off-axis that might still be within the sensor's narrow cone of pulses. A missed target will cause larger than expected position readings, often the distance to a wall in the background, while an interfering object will cause smaller than expected position readings. Consider factors affecting the reflection of sound from the intended target, such as proximity to sensor, size, angle to sensor, flatness, and hardness. If feasible, modify a difficult-to-detect target object to better reflect sound by making it larger, flatter, or harder. If you experience problems with small nearby objects like a cart on a track, change the sensor's range setting in SparkView or Pasco Capstone software from the default long range to short range. Finally, if you have unexpected velocity or acceleration readings, start your troubleshooting by viewing the easier-to-interpret position measurements instead.
Set the wireless motion sensor on a flat surface to measure an object moving horizontally, or rotate the sensor face to measure an object moving vertically above. Use the built-in hole and thumb screw to mount the sensor on a vertical support rod or on a horizontal support rod. Use the 1/4-20 threaded hole at the bottom of the sensor with standard camera accessories, such as a tripod, or with available Pasco accessories for mounting the sensor on a Dynamics cart, or magnetically on the ceiling. Finally, use the sensor's integrated clips to mount it on the end of a Pasco track.
The fragile gold-colored transceiver is both recessed and covered by a metal grill for protection, but be careful to avoid impacting it. For example, direct cart plungers away from the sensor. Protective accessories are also available, such as the elastic bumper and the motion sensor guard, both of which the motion sensor can see through without interference.
By default, the zero position is at the face of the sensor, and the positive direction is in the direction of the emitted sound pulses. However, in SparkView or Pasco Capstone software, you can both redefine the zero position and switch the sign convention for future runs in a particular experiment. You can also use the calculator feature in both applications to transform the sensor's basic measurements into others, such as speed or distance traveled, and even kinetic energy and gravitational potential energy for an object of known mass. To convert from round-trip pulse time to position, the software uses a default value for the speed of sound of 344 meters per second. In Pasco Capstone, you can adjust that value for your specific experimental conditions. At high sample rates, the derived velocity and acceleration measurements may get noisy. You can adjust how these measurements are derived in Pasco Capstone to reduce this effect. Finally, two sensors in the same experiment will automatically alternate their sound pulses to avoid interference with each other, though with a corresponding reduction in maximum measurement range. Visit the Wireless Motion Sensors product page at pasco.com for more specifications, accessories, experiments, support documents, and additional videos. Thanks for watching.